All right, so here are note 7.2, law of sines. Big thing with law of sines we got to understand is we're not dealing with right triangles anymore, and we're going to be dealing with triangles that are oblique. Two subsets of oblique triangles are your acute triangles, where all three angles are acute, or you can also be dealing with an obtuse triangle, where you have two acute angles and then one obtuse angle there. So, let's look at some of these examples here. So first, this law of sines is here, and you'll be given this formula always on a test. You don't have to memorize it, but realize that the side alpha, A, is always opposite your angle alpha. As C is opposite sigma, and then as B is opposite our beta up here. So it's pretty easy to prove the law of sines here, and we'll look at an example here. So what you want to do is recognize that for any triangle, you can always draw an altitude, perpendicular from one side to opposite vertice. You get your altitude. We're going to label it H. So what we can do is we can go ahead and write an expression for angle C and angle A using sine. So we have two right triangles. So we have, let's say, the left right triangle, and we have the right triangle. So for the right triangle, we see that we have a side A here. So we can go ahead and write that the sine of lambda, actually I'll go like that, is equal to, sine is opposite, so that's H, over the hypotenuse, which is A. Now for the left triangle, I'm going to do the similar thing and define my altitude and my angle alpha, and I'm going to see that the sine of alpha is equal to, again, my H over C. Now notice that H is not the hypotenuse, it's dealing with this altitude. If I solve these both out for H, I get H is equal to the sine of lambda times A, and this is H is equal to sine of alpha times C. Setting them equal to each other, because this is equal to H and this is equal to H, we get sine of lambda times A is equal to sine of alpha times C. And by dividing both sides by A and C, you can see where we get our expression, sine of alpha over alpha is equal to sine of sigma over, or I'm sorry, lambda over C. You can do the same thing to show sine of B over B if we just went ahead and, instead of using this diagram, we drew our altitude from this here, made it perpendicular, and we can show this. So with our sine of alpha and our law of sines, we need to understand we'll never use all three of these equations. We'll only ever potentially use two of them at any one given time. We don't want to deal with three equal signs. So either we're going to be dealing with sine of alpha is equal to sine of beta over beta, or we could do sine of alpha or sine of beta over beta is equal to sine of lambda over C, or you could do the other scenario where it's sine of alpha over alpha is equal to sine of lambda over C. We'll never use those scenarios. So through these types of problems with law of sines, we're going to come up with three different possible scenarios. One, we get one triangle solution, that we have one possible triangle where we create. Another option is if we have that we might get sides that could not create a triangle. And then our third option we could get is where we could actually have two different triangles. We'll call the ambiguous case. We'll deal with that more the next lesson. So let's look at a sample problem. So solving these, we're going to want to find all the possible. We need to understand triangles have three sides and three angles, so there's 6 possible unknowns. So for this scenario, we're dealing with an angle side, being we're given 2 angles and a side adjacent to those 2 angles. So we're given angle side. Remember from geometry that angle side does prove triangles congruent, so we will get a one triangle solution. So looking at this, we got alpha beta, so we still need to our unknowns are lambda, and then we need to know side B and side C. So I always encourage you to work off of things that you know that was given to you first. So if I want to use, I always look for something that I know both sides of my law of sine. That means I know the angle alpha and I know side A. So that sets up my sine of 30 degrees is equal to 5, which is a number. I can put that into my calculator, so I'm good with that. So I only want to solve this and have one unknown variable here. So if I want to, let's say, solve for side B first, I can do the sine of beta, which is 70 degrees, over B. I cross multiply, I get B times sine of 30 is equal to 5 times the sine of 70. Divide both sides by sine of 30, and I get B is 5 times sine of 70 over the sine of 30. So now I use my calculator to do 5 times the sine of 70 divided by the sine of 30. And we should always bring it out a couple decimal places. So I'm going to bring this out to 9.40, so approximately 9.40. So that's my beta. So now let's go ahead and find C. In order to find C, I need to find angle lambda first. So this was 9.40. So knowing I have 2 angles of a triangle, I can find my third angle by triangle sum theorem. So this is forced to be 80 degrees. So again, I use what I was given and set up my law of sines. And I have sine of 30 degrees over 5 is equal to sine of 80 degrees over C. I cross multiply, I get C times the sine of 30 equals 5 times the sine of 80. And I get C is equal to 5 times the sine of 80 over the sine of 30. Again, use my calculator. So I type in 5 times sine of 80 divided by sine of 30, and I get my next side, 9.85 approximately. So now I've solved for all unknowns of this triangle. And notice I should make sense of this solution and make sure things make sense. The angle, if it's a small angle, the smallest angle will open up to the smallest side. The next largest angle, which is 70 degrees, should open up to the next largest side, which is 9.4 degrees. And our largest angle, which ended up being 80 degrees, should open up to the largest side, which is 9.85. So verifying my solution like that. So in the second example, it's an example of angle side angle, where our side that we know is in between the 2 angles that we know. But you know, this proves triangles congruent, so it's only going to give solution and rise to one possible triangle. So again, I'm going to try and utilize things that I know. Nice thing about two angles, I can directly find my third angle using my triangle sum. So 60, 20 is 80. So I know that my lambda has to be 100 degrees. Okay, so from here, that is going to be my ticket for my law of sines because I know side lambda and angle C. So those correspond. So I have sine of 100 degrees is equal, or over 12 is equal to, now I can establish whatever other law of sines I want to use to find my unknowns. So we can find A first and do A over angle alpha is sine of alpha. And then I get, again, I'm going to use this kind of lock key here now that I have one of them established to find my B. So B, my beta is sine of 60 over B. So I'm going to pause it here. I'll go ahead and solve those out and make sure you can find the solution. And I'll post them here in a second. So pause your video and try it on your own. So you should see from this, I got a A to be 4.17 and a B to be 10.55. Again, smallest angle is 20 degrees, shortest side is alpha and A. Next largest angle would be 60 degrees. 60 degrees here, and my next largest side was 10.55, which corresponds to B. And I can see my largest side, C, corresponds to my largest angle, lambda. So our next law of sines problem is going to be an example of angle side side. So remember from geometry that angle side side does not prove triangles congruent. So this is where we're going to get oblique cases, and we're also going to get cases that do not exist. So for this one, we can try and draw the triangle, but this one's not going to work out, but we could have side C being 5, side B being 3, and then we see that if this is side B, angle beta is over here, being 50 degrees. So if we establish, since we have B inside B, we know we can do sine of 50 degrees over 3. And I can use that to help me find angle C, well, or lambda. So then C over sine of lambda, and my C, I know, is 5. So when I multiply this out, I get sine of lambda is equal to 5 times sine of 50 degrees divided by 3. So I get, so here's going to be a scenario where we possibly could get two triangles. Again, it's angle side side, so I don't know that the triangles are going to be congruent. So when I get down to this, I can set it up because I know my B and beta, so there's my lock key, and then I can fill in the rest, right side with the rest of whatever law of sine part I want to use. So I have 3 here, so I can go ahead and try and solve for lambda. So notice when I put this into my calculator, I get 3 times the sine of 30, 3 times the sine of 30 divided by 5, I get 0.3. So I get the sine of lambda is equal to 0.3. Well, the interesting thing we need to know is, remember, we could have obtuse or acute angles here, because triangles can be acute or obtuse, so they can have angles that are larger than 90 degrees. If I do inverse sine here, I only get one angle, my principal angle, quadrant 1 angle, that's 17 degrees. Okay? But we know that sine's also positive in quadrant 2, with a reference angle of 17 degrees. And I do 180 minus my reference angle, and I see that this could be also an angle of 163. So I have two possibilities here. I could have an angle of 163 and an angle of 17 degrees. So I got to see if it makes sense that it could be 163 or 17. Well, for this one, lambda could be equal to 17 or 163. But notice, our other angle here, beta, is 30 degrees. If this is already 30 degrees, 30 plus 163 is equal to 193. That's bigger than 180, which means this can't be a possible triangle, because we don't have any room for a third angle to add up to 180. So this eliminates that option. So here we just have one option of the triangle. So, in conclusion, it's really important anytime you are finding angles, you need to check to see if two triangles can be drawn, knowing that sine is positive in quadrant 1 and quadrant 2. So you'll always get your principal angle here as your reference angle from your calculator, which is just inverse sine. Okay, and then this reference angle over here is the same here. So to get this angle here, you got to do 180 minus your reference angle. So always make sure when you're using the inverse sine button, you check for these two cases. We'll work more with that next week. Enjoy your weekend.